báo cáo xong là mình bị kêu xuống dưới check out luôn, cho ra khỏi trại.
Rồi thôi, ok. Báo cáo tốt xong là coi như là làm quà cho
Xin
tụi
lỗi các
Kotlin
anh em
luôn.
khác. Không theo dõi được mọi người được.
Ok, được rồi anh Ngọc ơi, anh Ngọc có thể tắt màn hình ạ.
Ok.
Dạ. Có được 9 bạn attendee rồi. Ok, Thắng cũng dạ rồi, anh Triết Nguyễn vào rồi, chào anh chào mọi người nhé.
Chào Jack.
Rồi, ok.
Welcome to
VANJ2020. Tại sao là không thấy hình ta?
Dynamic Network in 2016, visioning a network where we can connect researchers and scientists between Japan and Vietnam. Welcome to VANJ2020.
Chưa thấy hình sáng
rồi.
rồi.
Hình đâu Thảo ạ?
Không thấy hình sáng rồi. Ok.
Dạ vâng. Có vẻ là
Không sao, anh có dự phòng đây rồi, cho nên nếu có trường hợp có gì anh sẽ bật của anh nhé.
Dạ vâng, như bây giờ lại được rồi.
Rồi ok. Rồi em đi. Rồi thì còn 5 phút nữa thì để anh bật lại cái màn hình đầu tiên của anh cho mọi người vào mới biết đúng session, đúng slide. Rồi bắt đầu cái anh bắt đầu thôi. Rồi mọi người nhìn thấy màn hình của Thảo chưa ạ? Rồi. Ok. The first author is Dr. Ngọc nhé. Ok. Ok. Rồi trong lúc chắc là mọi người chắc cũng thấy rồi, thì là lúc mà diễn giả phát biểu thì mọi người là vui lòng là tắt cái microphone và tắt camera của mình. Rồi và khi diễn giả trình bày xong á, thì ví dụ như là diễn giả khác hoặc là các vị tham gia thì có thể là đặt câu hỏi bằng cách là nhấn vào icon raise hand ở trong Zoom chat, hoặc là gõ trực tiếp cái câu hỏi tiếng Việt hay tiếng Anh cũng được trong cái bảng chat đó, thì chair sẽ hỗ trợ để chuyển câu hỏi trực tiếp đến cho diễn giả. Ok, ra đi một vòng nhé trước khi vào. Ok. Rồi, mọi người take a rest khoảng 3 phút nữa. Chúng ta có 10 attendee. Cho phép Thảo hỏi các anh chị em mà đang tham dự có nghe rõ mà, nếu nghe rõ mọi người gõ vào cái chat room á là cái chữ ok nghe rõ là được ạ. Ok, ok clear.
Thảo ơi, có thể make bằng core host để hồi bạn có thể share cái quyền điều khiển màn hình cho
Dũng. Sáng ơi.
Dạ vâng.
Em set bạn bạn Nguyễn thành core host đi nha.
Em set rồi ạ.
Set được chưa? Bạn kiểm tra lại thử bạn ơi.
Có bạn thấy rồi, nhưng mà
rồi bạn thử coi. Ở trường hợp mà lúc đó nếu nó ấy thì hoặc là ấy cứ trình bày luôn, rồi phần người còn lại trả lời cũng được nha. Người còn lại tham gia phần set QA thì người QA trả lời nha.
Chị sẽ chuyển cái gọi là chuyển cái slide nó không smooth lắm.
Ok.
Em cũng thông báo mọi người là hiện tại đang livestream rồi ạ.
Rồi ok. Rồi xin thông báo chưa đến giờ phát biểu, chưa đến giờ chính thức, cho nên là xin nhắc lại bằng tiếng Việt là chút nữa mọi người sử dụng tất cả bằng tiếng Anh nhé. Còn nếu như các audience, các vị tham gia mà có hỏi thì có thể ghi bằng tiếng Việt cũng được. Thảo sẽ dịch ra tiếng Anh và chuyển cho speaker. Rồi còn nếu như trực tiếp đặt câu hỏi bằng tiếng Anh thì càng tốt.
Ủa sao phải dịch cho speaker vậy? Speaker cũng người Việt mà.
Speaker không thấy anh, không thấy cái bảng, không để ý cái bảng đâu. Dạ. Ok. Rồi. Một phút nữa nha mọi người. Sáng chuẩn bị video cho em, video nhé.
Vâng. Em cũng xin phép record luôn nhé. Đầu từ bây giờ luôn ạ.
Ok, record đi. Mọi người cũng vào rồi đó. Ok. Okay, it ties. Okay. Hello everybody. I'm Thảo from Nagoya University, Japan. Today I am the chair of the session Role and Application of Power Converter, Energy Storage System, and EV in grid with high penetration of renewable energy sources. This session is organized by VPES, Vietnam Power Electronics Community, in collaboration with VANJ Vietnamese Academics Network in Japan. First of all, we would like to show the greeting video from the conference committee, please.
Welcome to VANJ2020. Vietnamese Academic Network in Japan, or VANJ, was founded in 2016, visioning a network where we can connect researchers and scientists between Japan and Vietnam to exchange their scientific knowledge while strengthening the relationship in technology and economy between the two countries. After 4 years, VANJ has become one of the largest academic networks of Vietnamese approach, with more than 2,000 members.
Each year, we and our partners organize international meetings and various seminars as a platform to truly bring everyone together. With the COVID-19 pandemic has been going on for a while, it is even more important to continue the scientific exchange and academic networking. So we set our mind to make VANJ Conference 2020 happen completely online to secure the safety and the health of all our participants.
On behalf of the organizing committee, I'd like to send our gratitude to all of the speakers that are joining us from Japan, Vietnam, or even from France, UK, and other countries. Thanks to their contributions, we are able to build 11 technical sections, focusing on many important aspects of science and technology. We hope that all of the participants will have a great experience and fruitful discussion, attain many more collaborations and academic networks.
Welcome to VANJ 2020, when we connect, communicate, and create.
Okay.
And a triathlon is set to take place next year with guiding the way and tracking performance. The event will...
Okay, and we return our session. In this session, we have a 5 presentation, and each presentation takes about 50 minutes for present, and after that 5 minutes for discussion, question and answer. We have a 5 presenter. The presenter from Vietnam, Japan, Kazakhstan, USA, and South Korea. This is the table and the order of the presentation. Before the session starting, I would like to introduce some regulation for presentation and Q&A session. The first one, when a speaker is giving his presentation, all the other speaker and attendee should be mute your microphone and turn your PC camera off. After a speaker finishes his presentation, if other speaker or attendee would like to ask question, please click the icon raise hand in the Zoom chat window. The chair will unmute your microphone for you to deliver the question. In addition, the attendee can write your question in the Zoom chat window. The chair will I'll transfer the question to the speaker when the presentation is finished. Now, I would like to introduce the first presenter, Dr. Trần Huỳnh Ngọc. He was a scientist in Toyota Technological Institute, Japan. He now currently with the Power Engineering Consulting GIS company in Vietnam. His presentation title is Impact of Renewable Energy on Power System. Dr. Ngọc, are you ready?
Yes.
Okay, please share your screen. I will turn off.
Okay, I'm sharing.
Yeah,
So did you...
I see your screen. Okay, please.
Yeah. Thank you very much for your introduction, Dr. Thao. Good afternoon, everyone. I'm very happy to present the topic of the impact of variable renewable energy on power systems to you today. So I put the additional words variable to clarify that I'm focused on solar and wind power, not include hydropower and other conventional, other synchronous kind energy source in my presentation. My presentation has 4 parts. The first one is the development of solar and wind power in power system. And before talking about the impacts of solar and wind power on power system, I will point out some main points, some features of wind and solar source. And the last one is the conclusion. So if we look at the development of renewable energy sources in power system, now they share about 26% of total electricity production in the world last year. And also we can see that some countries fully utilize, some countries fully utilize renewable energy to generate electricity. But it's not only wind and solar, but mainly hydropower. So if we focus on wind and solar, so we will see that its capacity, their capacity is about 50% and 57% of the total renewable energy capacity in 2020 and 2025 by prediction, respectively. So if we care about the solar and wind energy share in the total energy of the world, is around 8% last year and 9% in the first quarter of 2020. And in terms of power capacity, from the year 2000 until now, the share of solar and wind power in the total renewable energy increased from less than 5% to 20%. And last year, it shared 90% of the net renewable energy capacity expansion. In particular, in Japan, until last year, 63 gigawatts of solar power has been installed and sharing around 20% of the domestic generation capacity. And for 2030, a total of 64 gigawatt solar power and 10 gigawatt wind power have been targeted. In Vietnam, until last year, around 5.5 gigawatt of solar power has been installed, sharing around 10% of the domestic generation capacity. And in the national electric plant, 11 gigawatt solar power and 10 gigawatt wind power have been targeted until 2025. In terms of energy, in Japan, now solar account for around 8% of the domestic electricity production. And in Vietnam, they account for around 5% of the domestic electricity production, while just last year, they just account for around 2%. So we can see that within next 10 years, the solar and wind power in power system can take around like more than 25, 30, even 40% of the power capacity, and maybe around from 20 to 30 of the energy production. So at that level, they can cause some challenges for the power system operation. Now we will see the consequent impact of solar and wind power based on some main feature of them. So in comparison with the conventional power sources, the wind and solar have some different features. So in terms of primary energy, they are inexhaustible and renewable. So this feature will reduce the full utilization of the conventional power sources. And in terms of location, they can be available in many places, so they can be built in many places. So there will be distributed power source, many distributed power source. And this feature may have some good impact to the power system, like increase the using of local energy and changing the market model of our system. But it also cause some problem in the transmission congestion and reduce the transmission efficiency in both transmission system and distribution system. And it also cause some challenge in protection system, in the protection system, because the current protection system, especially in the distribution system, is suitable for the traditional power system in which the power flow just go in one direction. One main feature of the solar and wind power is related to their active power output. It's uncertainties, variability, and intermittent. So the weekly change in the active power output can cause the voltage fluctuation and then reduce the power quality. They also require smaller sampling time for the power system control, and they cause the imbalance between the demand and the supply. Then it makes some difficulty in the frequency control and in the voltage stability and control. In a middle, in long-term planning or in the middle term, it's also cause difficulties for power balancing. Another feature of the solar and wind power is that they connect to the grid by converter, especially for PV and variable speed wind turbine. So with that connection, they have zero or very low kinetic inertia. And by this feature, they also reduce power quality and reduce angle stability and primary reserve, which is needed to support system stability. So if we consider these impacts versus time scale and system scale, so we will see that they lie in a very wide range of the time scale and system scale in our system. So, example, the voltage management power qualities rely on the very fast time scale, and together with the distribution efficiency, I mean the transmission efficiency in distribution system, they belong to distribution level. Other impact is on the transmission system, so like grid stability, including voltage and frequency angle stability, is lie on the time scale around second. The frequency control is lie on from second to minutes or to several minute time scale. Or adequacy of power is an important issue for power system planning for a long time, in long term. So we don't have time to talk all about these impacts, so I will pick two examples to show you for the consequent impact of wind and solar power on power system. So the first one is the impact of PV on voltage management in distribution system. So we have done it 4 years ago with on the test system is a standard rural distribution system in Japan. Here we model the medium voltage and low voltage system together, and the load model is also very detailed. We consider two scenarios. The first one is large PV capacity at North City 4. It's almost at the end of the feeder. And another scenario is without large PV capacity, but distributed PV, around 5 kilowatt peak PV at every house of the low voltage system. So in total, we have 2.1 gigawatt PV power in the second scenario. The penetration of PVs increase the voltage profile. So like the voltage is increased more at the end of the line near the PV location. Even in the distributed PV, it's also high at the end of the line, and it violates the voltage requirement. So in this case, we try to apply 3 methods. The first one is power conditioning system power factor. The second one is upgrading the voltage level, and the third one is STATCOM. So in this example, I just show 2 methods because STATCOM explanation for STATCOM case is very complicated. So in this case, the both upgrading voltage method or apply a PCS power factor of 0.85 is effective to reduce the voltage to the requirement range. But in the case of the concentrated PV, just only with 1 gigawatt power at the end of the line, so even we apply a power factor of 0.85, so it could not handle the voltage. So this is example just very simple to say that we need to carefully handle the voltage in case of PV penetration. The second example is impact of solar power on voltage and angle stability of power system. So the test system is subject to the Germany standard VAR and 4105 2011. And in this test system, the solar power capacity accounts for around 45% of the total generation. The researcher applied a fault here in bus C1, and we can see the voltage response for the fault in the figure 11. So due to the fault, during the fault, the voltage is dropped and it's caused 1 PV unit disconnected after fault because it follows this standard. And then the imbalance in active power after fault have caused synchronous generation in the system is start to fluctuate, you can see. And even one synchronous generation losses is stability, losses is synchronized after fault. So these examples say that PV need to be improved in their response to fault. So that means some standard need to be improved, need to be changed, so that PV still can connect it to the system to support the system active power. But even with that improvement, PV still don't have the inertia. Wind power still have very low inertia. So we still need more other method, other supporting to handle the frequency and angle stability of the system. So far I have talked about the consequence impacts of solar and wind power on power system. But besides this impact, there are also good impacts by solar and wind power on power system. The first thing I would like to introduce is the concept of prosumer. Prosumer is a new concept in power system made by the participation of wind and solar power into the system. The word is a combination of producer and consumer. So the reasons for the appearance of prosumer is that many distributed solar and wind energy source, so that it might lead to the local energy utilization, and together with the digital technology, so it forming many prosumer. So this concept is a very basic and very important change in the business model of power system. From prosumer, by combination with many other techniques and other factors, it comes to a new structure of power system. So by the participation of solar and wind power at the distributed location, the boundaries of producers and consumer is broken in many levels in scale of power system. From a very basic prosumer like home prosumer, together with storage and communication technique, so it have to form microgrid, smart grid, and the power system become more flexible, efficient, and of course complicated. And in that transformation, wind and solar is one key factors beside other physical and digital technologies. So this one is the main point I would like to introduce you in one of the impact of wind and solar power on power system. Okay, so I would like to conclude my presentation here with 4 points. So recently, the solar and wind power source have been rapidly developed in power system due to many of their advantages, but they also cause many challenges in a wide range of time scale and system scale for power system. Besides, they also have to bring new concepts, new business model into power system, and they are one of key factors for power systems transformation. Thank you very much for your attention.
Okay, thank you, Dr. Ngọc. And we have one audience who would like to ask you some question. Okay, please, Mr. Nguyễn Xuân Di, can you hear me? Mr. Xuân Di.
Do you hear me?
Yeah, I hear. I hear. Please.
Okay. Yeah, I'm ready to talk with the speaker.
Okay, please.
Yes.
Yeah. Okay. Thank you, Dr. Ngọc. You present a very good topic, and I have one question for you. As you know, the solar energy is very good energy as new renewable. You know, in Vietnam right now, the solar energy develops very quickly. So you can give some idea about how develop solar energy is good or bad, because some people just say about the good advantages of solar energy, but not good. Not so much people mention. So from your opinion, you can give us some idea about the solar energy is good and not good. Thank you.
I think in my viewpoint, it's not suitable to say a thing is good or not good, but we need to consider it in a bigger picture, a bigger story. So you can see that I have presented the development of solar and wind power in the power system together with many challenges they cause to the power system here. So the people talking solar is actually not many. Not many of them is technical people. So technical people like engineers in EVN, they have a very good awareness of what PV can bring to their system, like I listed here. So they are now preparing to handle with this impact. So solar have some good, solar or wind have some good goodness, like they are renewable and clean, and due to this advantage, the power system try to utilize them as much as possible, but they also prepare to face, to deal with, to handle with the difficulties they can bring to the system. I can say that solar or wind power is unavoidable. We just need to prepare for their integration into the power system. So is that clear to you?
Yes, I see. Thank you so much.
Okay, it's okay for you.
Thank you.
Okay, Dr. Ngọc, we now go to the next question from Mr. Dương Trần. The question is that the EVN look into the modern technology such as SVDC for power transmission, virtual inertia for renewable energy power converter, and microgrid virtual power plant. Okay, do you understand clearly? The question is the electric Vietnamese company EVN.
He asking about that model in. I actually my company is not directly control the power system. We have relationship with the national LDC, but I just know that they are learning, they are studying, and they are prepared. They are preparing for story. At least World Bank and other countries like Denmark, Ireland, and Germany also support Vietnam to go towards the smart grid technology by providing many lecture, conference, and experts to support EVN to prepare for handle these problems and integrate new technology into the power system.
Okay, I think your answers is clear for the. Okay, the next question is from Dr. Đỉnh from Hanoi. Okay, Dr. Đỉnh, can you hear me?
Yes.
Okay, please give your question.
Okay, thank you very much for your very nice presentation. This is Dean from Hanoi University of Science and Technology. I have a question regarding prosumer. Yes, this slide. So could you show me some perspective of prosumer, where it is now? It is a concept or a reality?
Actually, it's a reality now. You know that in Vietnam there are. Reality now. You know that in Vietnam there are. Dr. Đỉnh, could you temporarily mute your microphone?
Okay.
So prosumer is a reality now. So many rooftop solar has been installed in many houses in Vietnam. So so together with the load, just only load and solar, they can form a very simple prosumer. if they can be integrated with energy storage, so the prosumer model will be more easy to be controlled or maybe give them more benefit. But in terms of technical aspect, just only a lot and a renewable energy source like solar or wind, it can form a model that can be receive energy when it needed and generate energy to the system when it's available.
Dr. Định, the answer from the speaker, the satisfied for you?
Yeah, thank you very much. But I guess we may need a brand new transaction model for that new kind of prosumer, right? New trading model. Do we have now? Or in the building?
New what? Sorry. New what?
Yeah, I'm asking about the trading model.
Trading model.
Trading model.
Yes.
So far, in some country in the world, the trading model based on prosumer model have been developed very well. Like in Singapore, they have peer-to-peer trading power market, or in some country in Europe or Australia. In Vietnam, now we don't have peer-to-peer trading power, but just only the trading power between home and EVN. So Vietnam, the trading model for prosumer is not how to say, it's not completely developed. But if you would like to see some more better, you can look at information from Australia, US, Singapore power system. In Japan, they also develop started.
Thank you very much.
Okay, Dr. Ngọc, we now remain 2 questions. Okay, please take in time. The first question is asked, why in the power plan 2025, they want to increase the amount of wind energy instead of solar energy from the Trần Gia Huy, Mr. Trần Gia Huy. Okay, please answer.
Okay. So in Japan, they started to develop solar power around 10 years ago, around 10 years, 9 years ago. So they applied the feed-in tariff. We just applied feed-in tariff around 2 years ago, right? In Japan, they applied it around 10 years ago. And they have a long time go with the feed-in tariff until 2018. So by that time, the volume of solar power is increased very fast. So far the solar power is, I think in Japan, they have been trying to utilize them as much in Japan so much, so that there are not much space or resource for it. But the wind power is still available more. So, and also by the decreasing feed-in tariff for 10 years now, the solar power trading in Japan had been changed from feed-in tariff to bidding like Vietnam just about to do next year. So this reason makes the solar power is not much attractive for investor. But for wind power, there's still room for it to be developed, and the feed-in tariff for wind power is still available. So it can attract many investor to invest into wind power in Japan.
Thank you, Dr. Ngọc. And the last question is from Mr. Xuân Di. Mr. Xuân Di, please. Can you hear me?
Yeah, yes.
Okay, please. Okay, please, short question. Okay.
Thank you. Actually, I third question, and then now it's the last one for me also. So I would like to ask a little bit question for Dr. Ngọc. As you know, when we develop solar energy, and one thing we remains about the waste from the solar energy, and you can tell how we can treat waste from the solar energy. That's a big problem.
You mean waste? I'm not okay. Thank you for your questions. But firstly, I have to talk. I'm not an expert in the waste, solar waste. But based on my knowledge, it's not much a concern, because in solar panel structure, just a little substance is not good, but other it can be recycled, can be recycled. So based on my knowledge, my opinion about that problem is not a very big problem. We just need to have a good plan and investment for it. One thing in Vietnam, people always call solar panel is bin.
Bin, yeah, yes.
But when we think about bin, we think about something very poison, very pollution. But actually, in solar panel, the pollution percentage is very, very small. So I think there's some knowledge about it. The people need to be corrected.
Yeah, I think have two things: the panel, solar energy, and inverter, in converter, like the pin. When you use and after, when you stop working, you throw in the environment, and so you need to give some method to recycle or treatment with the waste from the solar energy. Thank you.
So there are some research or some reports so that the treatment, the industry of solar waste treatment can have some profit.
Reasonable?
Yes. So, but like some report from IEA, International Energy Agents. Yeah, of course, it's just on, they are just on study, and we still need investor to invest more in the technology to deal with it. But theoretically, it can be done. It can be handled and can produce some benefit for the investor. For the investor, maybe many people here know about it better than me. So, Dr. Thảo or Dr. Định, could you support me to answer about the problem of treatment, treating the converter waste?
Okay, I can share some information. Yes, I know in the Vietnamese media now, many people concerned about the waste of the battery and converter. Yes, we know it have some problem, but according to Dr. Ngọc and also my idea, the waste of converter and battery is the problem, but not really big problem. Everything use the converter and battery, not only the solar or wind energy system. So if we want to have the comprehensive treatment and solution, not only for the energy renewable energy system, but also electrical vehicle, battery is the battery waste and converter waste is problem. And so it's not only the problem of the renewable energy system. So I think the first solution is that we have the new or efficient recycle methods to reuse or recycle of the battery and converter in the near future work. I think so. But in this moment, it's not really big problem because renewable energy, not renewable energy, but also electric vehicle and industrial application use the battery and the converter. Yes. Okay, just my private opinion. I just remind the time for the Dr. Ngọc presentation is finished, and Dr. Ngọc, we remain one question. But okay, I will transfer after the conference, and you will answer the Mr. Tông Thắc Đồng by email or by chat privately. Okay.
Do we have time now? I can answer now.
We don't have a time now. I'm very sorry. Okay.
Thank you very much.
Thank you, Dr. Ngọc, and attendee. Many questions, very interesting. Okay.
Thank you. So I will stop sharing.
Okay, please. Okay, and we turn to the next speaker. Okay, I would like to introduce the next presenter, Associate Professor Đỗ Đức Tôn from Nazarbayev University, Kazakhstan. And his presentation title is Some Control Issue and Control System Design for Wind Energy Conversion System. Professor Tôn, can you hear me?
Yes.
Are you ready? Okay,
yeah.
I will turn off my screen. Okay, please share your screen.
Okay. So now can you see my screen?
Okay, I see. Okay, please.
Okay. So good afternoon, everyone. It's my pleasure to be here to present my topic about some control issue and control system design for wind energy conversion system. Thank you, Professor Thảo, for your introduction. So firstly, let me introduce let me spend about 30 seconds to introduce about myself. So I graduated from Hanoi University of Science and Technology in training in 2007 and 2009, bachelor and master degree. And then I went to Korea to pursue my PhD degree and got it in 2014 and worked there one more year as a postdoc. And in 2015, I moved to Kazakhstan to be assistant professor, and now I'm associate professor here. So today, this is my my lab so far that we developed here. We have 3 PhD students. So I'd like to ask for here we have many Vietnamese young Vietnamese researchers. So I would like to first, if you interested in working the same area with me, so I'm very open to have a new collaborate with all of you. So let me start my my presentation here today. So here I am focusing on we see there are several control problems of wind energy conversion system, and my topic today is just focus on one control problem of them. That is control of the generator size of the wind energy conversion system. So here we focus on this problem. For this, first we see that for the wind energy conversion system, we have 4 reasons of the wind speed. So the first and the fourth reason that we're not working. For the speed with too small or too high, we cannot work. For too small, we cannot get the power. For too high, that is has some mechanical limit that limit the wind turbine to work. So mainly we focus on controlling the generator, the wind turbine in the second and the third reason. For the second reason, we control to get the maximum power. But when the power of the wind turbine get the maximum value, we have to control to get the maximum value, because higher than that value, the system is not stable, mechanically stable. So we have to control with other maximum power. So there is 2 different strategies for controlling region 2 and region 3. But mainly for controlling the generator system, we focus on the region 2. for the region 3, we control the angle, the pitch angle of the wind turbine. And my presentation today is focused on the control of region 2. And of course, it has some transmission, some to transfer to go from region 2 to region 3 and go back. Of course, there are some algorithm to do that. So here, this is one typical control system that that we designed. Here we have the PMSG. That is one kind of permanent magnet synchronous generator. And here we see that wind energy conversion system have several types of noise, of disturbance, and also this system is very highly nonlinear. So we have to find one way. We have to design a good controller. What is robust, have the robust to disturbance, robust to parameter uncertainties, and can handle the nonlinear well. So that is one control problem of the wind energy conversion system. The other things is the problem of wind speed. So we know that to control the wind, to control the speed of the generator, we have to know the wind speed. We have to know the wind speed. So the wind speed in previous work, they can use an anemometer to measure it, but then the quality is not good enough to have a high performance control, feedback control for generator. So in some other literature, they use the observer, or the use the observer, or they use some other estimation technique to estimate the wind speed in order to control the generator. One of the technique is they not estimate the wind speed directly, but estimate through the aerodynamic torque. So by estimating aerodynamic torque, we can also calculate the wind speed. So this approach that I use in some of my publications. So here, this is some basic equations for wind energy conversion system. We have the wind, we have the power capture from by the wind turbine. That is one thing is important thing is the CP. That is a power coefficient that we have to get. Typically in the region 2, we have to get CP maximum. So CP is a function of lambda and beta. Lambda is a pitch ratio. It defined here, and the pitch angle, beta is a pitch angle. So we have to, in the region 2, in order to get the maximum power, we have to get the CP maximum. CP is given by the manufacturer. The equation and the curve given by the manufacturer. So we for each kind of wind turbine, we can know by observing the curve or the equation, we can estimate the maximum power for CP and associate with some one optimal value for lambda optimal. And some other thing is radius of the wind turbine, and this is the wind speed. So aerodynamic torque is defined by a PA, the aerodynamic power divided by omega t. That is the speed of the wind turbine, angular speed of the wind turbine. And we have the optimum reference for the wind speed working in the region 2, as I indicated before. And we have the gearbox ratio to transfer from the speed of the wind turbine to the speed of the generator. Also, the same ratio applied to the aerodynamic torque and the electromagnetic torque of the generator. So for the PMSG, EBU PMSG, we have this kind of equations to control the speed. So here we have in terms of control problems, we have omega TE and ID here as a state variable, and TA here as a disturbance. This comes from the wind turbine. And we have some other disturbance, that is DQ, DD, that is including the seasonal uncertainties and some other disturbance in the electrical part of the generator. Here we have a detailed equation for that, and we will transform this equation into the aerodynamics that we can apply the control. So here we use one kind of non-linear optimal control method. That is, we will transform the original dynamic system into appropriate form, to design the controller. So here we use a kind of we call the SDRE based integral SMC. That is a state dependent recursive equation based integral slide mode control. So this is the system that we transform it to. So in the SDA based integral SMC, we have two terms. One term is the optimal control law. The other term is integral SMC term. So that theory comes from the common theory of optimal control and optimal control based integral slide mode control. So we have some introduction about that. I don't know if I have time to do this, but then I can come back to this later because it's all this related to the control theory about the LQR, how to design LQR, how to design the state dependent recursive equation based control, and then LQR based for integral SMC. Yes. And then SDRE based for integral SMC. So we have several evolution of this control method, several steps to design to understand this. And to estimate the aerodynamic torque and some other disturbance, we have three types of disturbance. We have TA, we have DD, we have DQ, three disturbance terms that we defined before. So each of them we will build a kind of high order observer. Why is this high order observer? Because we know that the wind speed changing quite randomly. So consequently, the aerodynamic torque also change randomly that we cannot know its behavior. So it's a disturbance and sometimes it's very high frequency. The other thing is some disturbance in the electrical part also. Some of them can change very fast. Or the constant torque in the electric machine, or some PWM related noise or disturbance. So that's why we use a kind of high order observer in order to estimate the disturbance more correctly, to feedback to the control system, to give information to the control system to design, to get this information more correctly and to control it more precisely. So here, this is some kind of the result, that I present for this. So in this paper, I designed the kind of SDA based ISMC, but I have several others in the same topic that I applied different control method, different kind of observer, and with different system from the simulation to the experiment. So here we working with in my group or some other collaborators in Vietnam or in UAE or some other place. So yes, so if I have time, then let me talk more about the LQR and LQR based control. Yes, Professor Thảo. Yes.
Okay, a brief introduction is okay.
Okay. So about the LQR. So we know that LQR is stand for linear quadratic regulators. We have the linear system, and we apply the control method for this linear system. So the optimal control is a defined kind of function. This function relates to the price of of the control performance and the price of the control effort that we use, and then we combine together with the gain Q and R. So if we increase the Q, it means we consider the price. We very care about the control performance. Is X should be go to 0 as soon as quick as possible, as small as possible. It should be as small as possible. And if we increase the R, it means we focus about the control effort. It means the control effort, the control signal is very high to produce. So we need it to be small. Yeah, we need control signal to be small. We can control it. We have to control it, but we need just small. We just have a small control signal. So this is how we define J, and by tuning Q and R, and depending on the requirement or limitation of our system, we can choose appropriate Q and R. So in this theory, they say that the control theory, the control system, the control signal for the control law for this optimal control will be defined in this equation. That's R that we choose. B is a gain related to the control, and P here is a solution of the equation of this equation. That is, if we know A, B, Q, R, then we can solve for P. That is called the Riccati equation. And because of all of this term, A, B, Q, R is the constant. So we call this algebraic Riccati equation. In order to differentiate this to the state-dependent Riccati equation. So this equation can be solved very easily by one command in MATLAB. If we solve for P, we use this CARE with ABQR to solve for P. Very simple. And here I already write. So or we write or if we find directly for the gain K, feedback gain K, we use the LQR command. And this how to choose Q and R. So basically, each of element of Q and R is related to one state variable. So Q1 it related to performance of S1, and similarly for Q2, Qn, and R1 related to the control signal of E1. So we see that if we tune Q, Qi, we tune Ri, then we can tune the associate state variable or control signal. SDE is an extension of the LQR technique that is applied for nonlinear system. Before we have linear system, but now if A and B or at least one of them are nonlinear, so we cannot solve that equation directly. Riccati equation now becomes state dependent, so we cannot solve it directly. So we have to find the technique in order to solve that state dependent Riccati equation. And state dependent Riccati equation is come to this equation to solve. We have to solve this equation. We call state dependent Riccati equation. Basically, in general, this question cannot be solved directly, so we have to use approximation technique to solve this. But in some system, which is B is constant, then we can transform it to more easier form, approximate form to solve. So one of them is explained in this paper, nonlinear feedback controller and compensator. So and luckily PMSG can be explained, can be transformed into this form. So we apply this method to solve. So there's a lot of equations that I don't want to talk in detail, but we can approximate it into this equation. So basically, we have to solve one Riccati equation, set algebraic Riccati equation, and some limited set of the Lyapunov equations. We can use this. We can solve this easily by MATLAB. So Lyapunov equation we can also solve similarly to Riccati equation by one command. So with the PMSG we can solve this. We can transform to this form and to can approximate the solution. By this form. Yep. So this is a state dependent Riccati equation. And then we have the integral ceramic control. So integral ceramic control, basically they based on they have two terms. One term is a nominal control, and the other term is a switching control. So nominal control here, they use different control method to solve, and one of the famous one, the most popular one, that is they use the optimal control to solve for U0. And here I explain how we use optimal control to find for U0. And then from U0, after we find U0, then U1 we design based on U0. After we find U0, we can find U1 based on U0. So we have two terms. So for why is it integral ceramic control? Because it can deal with the disturbance better, because optimal control have the issue when the disturbance is not Gaussian, it's not white noise, they cannot handle it. So integral ceramic control can handle it. So that's why we move to ceramic control, integral ceramic control. And this also, because of U0 here based on LQR, then it's only only applicable for linear system, but with disturbance, linear system, but with disturbance. So in order to transform this to the nonlinear system with disturbance, we will extend it to the SDA based slide mode integral ceramic control. So that's why we use this. So similarly with the transform from the LQR to SDIE, we transform from LQR based ISMC to SDIE based ISMC for the nonlinear system with disturbances. So this is the theory behind this. Yeah. So and for the higher observer that I already explained. So here to conclude, we design a kind of control system for nonlinear control system for wind energy control system for the generator size of the system, not all the whole system, but we focus just on one part of the control system, that is generator side. So thank you.
Okay, thank you, Professor Tong. Okay, any question? Attendee and presenter, author presenter, any question? Okay. May I have a question, Professor Tong?
Yes, please. Yeah.
Okay. You present some kind of control methods, for example, LQR and integral sliding mode. Okay. What is the efficiency of the integral sliding mode as compared to the LQR? Yeah. I'm interested in for the sliding mode, integral sliding mode, and the NQR, traditional NQR. What is the difference and the advantage of the integral sliding mode control compared to the NQR? Okay, please.
Yes. So the LQR is very famous one that is focused on.
Yeah. Okay. Please continue.
This focus on for linear system, okay. But for linear system only, and without like disturbance. This only deal with the white noise. If the noise is not it's a disturbance, it's not white noise. Like if the system has some parameter uncertainties, the LQR is very vulnerable to that parameter uncertainties. So for the ISMC, that can deal with the disturbance, matched disturbance, and also some kind of unmatched disturbance.
Okay, I clear understand. Okay, the next question for the presenters is from Mr. Tôn Thắc Đồng. The question is that how is the effectiveness of your observer at low speed compared to ultralight extend Kalman filter? What lowest speed did you get? It is okay.
Lowest speed.
Lowest speed. What is the effectiveness of your observer compared to the other observer For example, extend Kalman filter.
Mhm.
Okay.
So
And what the lowest bit did you guess? Did you consider?
So
Okay.
yes. So
Okay, please.
yeah. The high order for the kind of typical observer. They have one to design. I think including the gamma filter. They typically consider that the disturbance is slowly varying. That is disturbance is derivative, time derivative can be considered as 0. To design observer. But the high order observer, they don't use this assumption. They say that disturbance is the time derivative can be different from 0. So that is a high order observer.
Okay.
So this is the main different things. That is, we have one assumption can be wave can be released. One limitation from theory. I talk here from theory point of view, because some of them some of the disturbance is quite like high time, like very high time varying the signal, but still people still using this kind of assumption to design observer and still working fine. But here I'm talking from the point of view, from the theoretical point of view. And next thing is about the lowest speed.
Yeah, the lowest speed did you consider in your observer?
Lowest speed.
Big is mean the wind speed. Yeah, I think so.
Yeah. So actually, even here, because wind speed here, I do together varying. So it depends on the system also, because the wind speed it depends on the wind turbine. Yeah, I simulate different kind of system. So I didn't aware of lowest speed, but it depends also on the system requirement. So I actually I don't like aware of this lowest speed here, but it already belongs to the system. The system, the limitation of the system, they define what is the limit for the system to simulate to start to work. Yeah.
Okay. Mr. Tông Thất Đồng, can you hear me? Is this okay for you? Okay, might be okay. He answered that he clear. So okay, thank you very much, Professor Tong. Okay. Okay, now answer no question more. Yes. Okay. Okay, Dr. Tong, I have a very short question before close your presentation. In your control system, you now apply in simulation only, and in the future you want to apply in the experiment system, right?
Most of my part is do the simulation, but then I have one paper that is we use a kind of hardware in loop simulation.
So you
in this paper.
Okay.
We collaborate with UAE scientists in Khalifa University.
Okay, I clear. And the very last question, you introduce your lab and you welcome Vietnamese students to participate in your lab. Do you or your university have some scholarship for Vietnamese students to study master or PhD degree in your laboratory? Okay.
Yeah. Thank you for your question. So yes, so Nazareth City here we open for foreigners for 0 years, 2 years ago maybe, for master and PhD degree. So here we have the very even the university is quite newly established, but we have a good lab, good facilities, and we have the good, like very good, very promising, very good package for the student, international student. But so far we have just some students from Pakistan, from India, from Iran, but not from Vietnam. So I hope in the future we have some students from Vietnam to work with me. Even in or can join another institute. Even not work for me, but it work in another lab, another majors. Yeah.
Okay, thank you very much, Professor Tong. Okay, your presentation is very interesting. Okay, please turn off your share screen. Yes.
Yep.
Okay.
Thank you.
Okay, and the next presenter is from USA, Dr. Nguyễn Anh Dũng from Virginia Tech and Mr. Nguyễn Lê Huy Bằng from Clarkson University, USA. And the presentation title is Power Converter Enable Electric Vehicle Grid Integration. Okay, Dr. Dũng and Mr. Bằng, are you ready?
Excuse me.
Dr. Dũng and Mr. Bằng, are you ready?
Dr.
Yes.
Tao,
Yeah, okay.
I have a request. It is okay?
Request. What request? What request?
Because I have some students here. They are very interested in the presentation of Dr. Zhou. So can it be in Vietnamese? Because I think all the audiences are Vietnamese. So could you give the presentation in Vietnamese, please?
Okay, it depends on the presenter. Okay, presenter Dũng and Mr. Bằng will decide. The presentation will be given in English or Vietnamese. Okay. Dr. Dũng and Mr. Bằng, what are your opinion?
Actually, like it's a hard questions. You know, like yeah, we prepare everything is in English, so yeah, if possible, like we can give another seminar or another talk in Vietnamese with Dr. Din's student later. Yeah, it's okay. But now like we all prepare in English, so I'm sorry about that.
Okay, Dr. Din. Maybe in this conference we will yield out in English, and after this conference, Dr. Dũng will give us a separate meeting or conference with your student in Vietnamese. Is this okay? Okay, Dr. Dũng and Mr. Bằng, please.
Okay, so first of all, we would like to appreciate the Professor Thao and the Vietnam Academic Network in Japan for inviting us to join this conference. This is a very great conference, and we have like a chance to create a network and then talk with other people. And yeah, we wish like the conference will be a success. And my name is Dũng. I'm from the Virginia Tech in the Future Energy Electronics Center, Virginia Tech. And today, like my co-presenter is Mr. Bằng. He's a PhD candidate in the Clarkson University in the US. So today our topic will be the power converters enable the electric vehicle grid integration. And firstly, Mr. Bằng will discuss about the vehicle grid iteration. Yeah, and please welcome Mr. Bằng.
Yes. Thanks, Dr. Thao and Dr. Dũng for very nice introduction. So I would like to present my part, the vehicle grid integration. So you can see that in the slide in the projected number of vehicles in the future. So it's predicted that by 2022, the electric vehicle will cost the same as their internal combustion counterpart. So that is the point of lift off for the sales. And it's projected in 2040, the electric vehicle would account for like 35% of all new vehicle sales. And you know that in many states and cities, they may ban the gasoline or the petrol electric vehicle. No, not all the not all the vehicle, but the car new cell in very near future, like 2030. In California, they ban the new cells for the gasoline car. So the electric vehicle, just like on in irreversible trends here. So what is the impact of electric vehicle with respect to the grid? So you can see in the figure here with the flat tariff, that means we don't give any benefits for people that use the electric at the high peak here. So this is the load curve. We usually have the very high demand in the midnight when all people get home and they turn on many electric devices. And here we can see that the electric vehicle can increase the bit load like in the maximum like 30% here. So this is the this is the data. If we assume that we have 150 homes with 2 vehicles per household, and with 25% of electric vehicle penetration, that means 25% of electric vehicle they will be charged when they get home in this time. So when we use the times of use rate, that means if you charge your car in the low demand period, like here in the very midnight here, so they will cost you very low money. But if you charge your car in the big demand time, the cost of charging is very high. So that will encourage people charge their car after the midnight with the low bit demand here. But it still can just reduce the bit loss in 16% here. So the electric vehicle will increase the bit loss in the loss curve here. So electric vehicle can be a trend that will hurt the loss, or can be an asset that will support the loss by our users. So we usually say that the electric vehicle can turn red or turn green. For example, in the left picture here, you can see that if we just get home and we charge our car at home, or even in the morning when they can be increased in the bit load at the morning by the electric vehicle also. If we charge the car at that time, the bit load can be increased more and more. But if we use the car as like energy storage system, and we can release the energy at the bit load periods of time, and we charge the electric vehicle in a very low demand time here. We will give the benefits to the grid and also the benefit to the car owner also. So people will like introduce the concept that VANJ2020, that means the unidirectional control charging. So first, we want to charge the car at a low demand time to give the benefits of low cost for electricity. And the second concept is the electric vehicle to homes or electric vehicle to buildings. That vehicle will act as a power supply to the home. They can be the backup power also. And a very new concept introduced recently is the electric vehicle to grid. The smart grid will control the vehicle charging and return the electricity to the grid, and they can also provide the grid service like frequency or voltage regulation or control. So for the roadmap, first by the introductions of electric vehicle to the race, we have the smart charging first. That means we just have the unidirectional power flow, and we want to minimize the charging cost based on the time of use. And we avoid, usually we just avoid the peak demand, but utilize the off-peak periods of time. And for the next concept is the vehicle to home or vehicle to building. The electric vehicle can be the smart buffer if we have the bidirectional power flow capacity. We can use that car as a backup power supply, and it will increase self-consumption of homes or buildings. And the final one is the electric vehicle to reach the V2G. We can use electric vehicle battery to provide some bridge service and reduce the bridge demand at a very large scale. So this is some study that how the smart charging or the vehicle to reach concept can bring the benefits to the grid. For example, the study from IRENA here with the scenario of 50% penetration in an isolated system with like 27 solar share here. So with the uncontrolled charging, the bit loss will increase by 9%, and we have the 0.5% of solar curtailment. The curtailment, that means we have more than solar capacities, but because of the demand and because of the power system already, the light transmission system and distribution system cannot handle all of that solar power at that time. So for the smart charging, we can reduce the bit slot from 9% to just 5%, and we don't have any curtailment in the solar generation in this case. The next scenario here, we have the 23% penetration in US, like California or Hawaii, Minnesota, New York, and Texas. If we don't have the smart charging and the loss will be increased 11% in the bit loss. But with the smart charging, it reduced to just 1.3%. Yeah, the next is the toll gas. The next study, if we have like 100% penetration of electric vehicle in Denmark, Germany, Norway, or Sweden, the bit loss will increase by 20%. But with the if we apply the vehicle to this concept here, it's reduced by 7% here. Yeah, in other scenarios, also we can see that we have the reduce in the curtailment of variable renewable energy resources, and the big lot also if we use the smart charging, the vehicle to reach concept. And the landscape in the future just look like in this slide. So the smart building will connect to the electric vehicle, and at home we also have the bidirectional power flow between the electric vehicle and the home. In the parking lot also, because in this slide they concern also the communication, so they boost the vehicle to vehicle communication system here. And in charging station or in the EV battery swap beam station, and they will connect to the transmission system and the generation system also, and all the information from the building, the house, the parking lot, and all the electric vehicle system, the charging station, they will collect in a data center, and the control center will control and analyze on these information. And so in next part, I will tell a little bit about the power electronics for electric vehicle charging station that forward to the vehicle grid integration. So for the charging charging station that interface the electric vehicle with and the grid. So usually we have the AC coupled station or the DC coupled station. In the AC coupled station, we have the transformer here, and we have some AC/DC converter, DC/DC converter, and we may have the BVs or the energy storage here, and with some converter that give the bidirectional power flow between the electric vehicle, the storage system to the grid. For the DC coupled station, this will the main distribution line will be the DC voltage here. And in Tesla supercharger station in Mountain Views, we can see that they use the AC coupled station here with with a transformer here, and they have a distribution panel port here, and they also have the stationary storage here with the many supercharger here. And in this slide, I will just introduce quite quick about some converter that can be used in the charging station. For the bidirectional AC/DC converter, we usually apply the power factor correction converter in here, and in the top of the slide, we have the interleave totem point power factor correction converter. They can provide the bidirectional operation, and they can also achieve high efficiency, and this is also suitable for onboard charger. And in the lower figure here, we have the multi-level voltage structure of the neutral point clamps power factor correction. Here we have two active switch for the 400 volt, and also two active switch for the minus 400 volt here, line here, and some diode. And because it have the multi-level voltage structure, so it can reduce the DVDT stress and EMCs, but we need to use more number of devices. And for the bidirectional AC DC converter at high power, we may have to use the active NBC with 3-phase here, and the T-type NBC here. So Dr. Dũng will continue the presentation. Dr. Dũng.
Okay, thank you. So
let me. Okay. Oh, I cannot give the control to you.
it's okay. So can you have me move to the next slide?
Okay. So just tell me, and I will move this slide.
All right. All right. So Mr. Bang already talked about the AC coupled converter, like AC couple station for the grid for the EV charging. So for DC couple, DC, that means like the input will be the DC and the output will be the DC. And typically, like as you know, the dual active bridge converter is mostly used in many applications. Yeah, I think most of people here knows very well about the dual active bridge here. So the advantage of this DAB converter is the substitution capability, and that it can achieve the very high efficiency with very high power density, because you can see here it's very simple. And the voltage ratio can be controlled by the transformer. And then the next will be the next will be the LLC converter, and because like we need the bidirectional flow for the power transfer, so that's why we usually use a CLLC resonant converter. And with the CLLC converter, we have two resonant tanks, one in the primary side and another one in the secondary side. By this kind of configuration, we can allow the forward flow or reverse flow with the resonant frequency. And because it's a resonant converter, so we can achieve the ZVS turn on, ZCS turn off, so we can maximize the efficiency for all the power level. And as you know, like for the future charging station, yeah, we are researching in the solid state transformers. Typically, for the conventional configuration, the transformer usually use the utility grid frequency, which is very big and then like it's bulky. So in this case, people like we focus more on the transformer to reduce the size, and after that we can reduce the cost. So we developed the high frequency transformer as a single solid state transformer here. So with the high frequency transformer, we can easily reduce the size of the transformer. And with the high frequency transformer, so we can apply some like higher device like wide bandgap device or silicon device to improve to increase the frequency and improve the efficiency. So what's the benefit of the solid state transformer? We have to consider into two factors. The first one, if we are the vehicle owners. So if with the vehicle owners, we usually want the cheaper charging. Like every time we charge our vehicle, we want to pay like as less as possible. So the solid state transformer can allow this benefit. And for the station owners, like we want to reduce the cost to install the station. So the solid state transformer, because it's in the high frequency application, so the size of the SST will be minimized, and then the efficiency will be quite high. So like it will be benefit for all the vehicle owners or the station owners. Yeah, next. So for the some topology, some configuration can be used as a solid state transformer. So the first one is the two-state solid state transformer with the AC DC in front, and then the DC DC in the end. So this is a two-stage. So we just use the rectifier plus with the dual active bridge, DAB converter, to produce quite high efficiency. And then the second one we can consider with the AC/DC isolated boost here with the high frequency transformer in the middle. And then the third one is the AC/DC dual active bridge here, also with the high frequency transformer in the middle. Yeah, next. So another topology is the modular two-stage SST with the 4-level rectifiers and 3 DAB converter. As from here, we can see the primary side of the DAB converter are connected in series, while the secondary side are connected in parallel. So in this case, we can reduce the DVDT, or we reduce the voltage stress on the primary side MOSFET. Yeah, because the high voltage DC link here is about 11.4 kilovolt. So it's very high for the power device. So by this configuration, we can reduce the voltage stress for all the MOSFET easily. Okay. So when we apply for the solid state transformer in this application, so we want to work with the very high frequency, like to reduce the size of the transformer. And then with the high frequency, like we have two candidates. Recently, we only have two candidates. The first one is the silicon device, and the second one is the wide bandgap device. So silicon device has been using for about like 20 years. And for the low voltage, low current, as you can see from the right curve, the low voltage, low current, we basically use the silicon MOSFET. And with the high voltage and high current, we use IGBT. However, the MOSFET and IGBT are quite big, even though like when we compare with the traditional MOSFET, it's still small. But in the modern application, it's like, because like the room for the power converter is very limited. So we need the the size of the power converter as small as possible to fit into the space. So the silicon MOSFET and IGBT now is quite big in comparing with the size of the power converter. So currently, like we have like all the choice, the gallium nitride or the wide bandgap device. So the gallium nitride is usually used for the low voltage and low current application, like below 100 ampere and below 650 volt. We usually use the gallium nitride. And then with the gallium nitride, because of the wide bandgap, so we can go the frequency as high as we can with the very small loss. And at higher voltage and high current, we typically use the silicon device, the silicon carbide MOSFET. So with the silicon carbide, it's also the gallium nitride, but it's designed for the high voltage and high current. And currently, like we have all the part like still under researching. We call the gallium trioxide. This one will allow with the very high voltage and very high current. Yeah, and another material go with the gallium trioxide is a diamond. Yeah, it's very expensive, and aluminum nitride, and they are still under development. So we hope like it will be released early. However, the gallium nitride and silicon carbide have been used in the commercial product. Yeah, next. So as you see, the Tesla Model 3, they use the silicon carbide MOSFET already. So in comparing with the traditional IGBT, like the silicon IGBT here, the efficiency is improved a lot, especially at the light load condition. So at light load condition, the efficiency, the loss is reduced by 80%, more than 80% easily. This is because of the wide bandgap material. So in this case, the wide bandgap device is like they will allow with the lower driving loss, with the lower RDS on to reduce the conduction loss, and with the lower COSS to reduce the switching loss in comparing with the silicon IGBT. And additionally, with the silicon carbide MOSFET, in comparing with the IGBT, it's about more than 25 times smaller. So in this case, the size of the power converter will be small, and that it allows the high frequency because of the loss. So when the frequency is higher and higher, the design of the magnetic will be smaller and smaller. So the total volume of the power converter using the silicon carbide MOSFET in comparing with the silicon IGBT is about like more than 10 times smaller. So the wide bandgap device is I think will be like the future of the power converter in any application. Next. Yeah, in conclusion, many progress must be done before the vehicle grid iteration come to practice, because it requires a lot of the research and require a lot of the testing, the experiment, and even the material material aspect. And then advance in power electronics, yeah, is definitely enable the VGI future. Yeah, and especially the wide bandgap device will be the future of the most of the power converter application, even though now it's still under developing. Yeah, thank you very much.
Okay, thank you very much, Mr. Bằng and Dr. Dũng. Okay, any question for the speaker? Everybody? Are there
Yes,
any
I have a
question?
question.
Yeah, please.
Yeah, thank you very much for your very nice presentation. So in slide 17 and 18, you mentioned about the DAB converter and the wide bandgap device. So my question is, in your system now, with the very high voltage like the 11 kilovolt, so I mean, what's the power device for this system? And do you get any issue with the very high voltage like this? Yeah, thank you very much.
Okay, thank you very much for your questions. Actually, in this one, you can see the primary side is in series. So with this configuration, we can reduce the voltage stress on the every MOSFET. In the commercial product, currently they use IGBT. Yeah, and in case if we want to employ the wide bandgap device into this application, 11.4 kilovolt, we can easily config more phase to reduce voltage stress, 11.4 kilovolt, and then the maximum if we want to use the silicon carbide MOSFET, so it's about 1.2 kilovolt, so we can easily put 10 of them. Yeah, that is the key to do with the silicon carbide device. But however, in the future, when the gallium oxide is released, so we can easily go up to 11.4 kilovolt with only one stage, and I believe that day will be soon.
Yeah, thank you very much.
Okay, any more question? Okay, can I have some question? Okay, Dr. Dũng, I have a question about can you return the raw mass of the wide bandgap device? Yes, the slide of the raw mass. SIC, SIGBT. Yeah. Okay, this slide. Yes, I'm very interested in the wide bandgap device. Okay, I have a example to share with you. When I apply a research proposal for the research fund, I would like to use the SIC and ZIN for my motor system and the high frequency power converter. I propose some topology and also some control methods to optimize the efficiency of the SIC and ZIN. But a professor in the committee, he said that many people now focus on the wide bandgap device. But you also focus on the trend. It is good or not good? And the wide bandgap device have a many problem for design, for application, and for control. And the reason why we should focus on the trend. Can you give me some suggestion or opinion?
Okay, thank you very much for your questions. So as I understand from your question is you would like to apply the SiC, the silicon carbide GaN device into your system for the motor control. Yeah, actually the GaN device, like now we are still doing a lot of research related to the GaN device because it's very sensitive. Yeah, and it's very hard to do like in the real application, because if like when we work with the hard switching and soft switching, they are very huge different, especially in the motor control.
Yes.
So for the wideband gap device, because of the fast electromobility mobility, so like it's very sensitive with the noise. So especially like at high voltage when the DVDT is higher. So in this case, like actually for me, I think like in the motor control application, it's still under researching, and I see a lot of researchers still doing it. But I believe like it's a very good topic to do, and we still have some hardware to do some like prevention or something like to protect the GaN device. Yeah, so I think like the GaN device for the motor control in silicon carbide for the motor control application will be the very good topic, and it has a lot of problem. But the trend is that I believe so, because with the silicon carbide device, like the loss will be minimized. Yeah, if we do it well, the loss will be minimized.
Okay, just an additional comment from Dr. Dương Trần in Singapore. He said that yes, the keyword is the soft switching for wideband gap. Are you agree with him?
For me, it's not. For me, like the soft switching for wideband gap device is only a part. The keyword for the, as I know, like, and I also discussed with some professor and also with some people from the EPC and GaN system. So the keyword for the wideband gap device actually is a thermal. It's truly a thermal.
Okay, thermal problem.
Because as you see, like with the silicon device or traditional MOSFET, when you give them 1 watt loss, it still survive because it's big, and then it's easier to do some like to do some heat sink or add some like thermal pad or anything like this to reduce the thermal. But with the wideband gap device, because of its characteristic, it's so small. So when we apply 1 watt there, like for example with the GaN system device, 1 watt will increase about 80 degree, more than 80 degree.
Okay, thank you. I have a question for Mr. Bang. Can you return the slide with the integration system with the EV? Yeah. Integrate system with the EV. Yeah. Best more.
What?
Yeah. This system. Yeah.
Can you say the number, the slide?
Okay. No, the best. For continue. Number 8. Okay. This.
Number 8.
Number 8. Yes. This one. Okay. This is the vehicle grid integration in USA, right?
Actually, it's just a national landscape. That means people just design that, and
you did that. So okay.
This from the Jiangsu. Yeah, he present this concept in this actually communication magazine here. It's not a real practice now.
Yeah. Okay, but in the future, do you think that this system will be useful and can be realized in the application or in the physical system?
Yeah, for the roadmap now, people already finished the smart charging concept. That means the V1 grid, V1G, and for the vehicle to house, we also have that in process. Yeah, but some concept like EV battery swapping station is not in practice right now, and for the smart pooling and packing slot with the bidirectional like bidirectional power exchange between the electric vehicle and grid. It's not in the practice, yes, but we hope that in the future it can become practice. Yeah, like just in the some slide, you can see that the electric vehicle can be a trend that hurt the grid. But with this concept, we can use the EV like a distributed energy storage system, and that will support the grid and also can even provide some grid services.
Okay, thank you for your explanation. And Dr. Hà Nguyễn, he had a question. Dr. Hà Nguyễn, can you hear me?
Yes, thank you.
Okay,
I
please.
just joined the seminar a little bit late, so related to the GAN device that maybe the other presented before. Mostly, I thought that this is just used for the high power and high voltage application, and that is not very familiar to me. But related to Dr. Bang's presentation here, so I think that yes, the structures of the system, like on the slide number 7 that you asked him before, I think that belongs to the system simulation. So frankly speaking, I don't have any question at the moment.
Okay.
Yes.
Okay, any more question? In writing the question from the audience, Dr. Dương Trần, he have an additional comment. The comment is that soft switching can provide 99.99% efficiency. This is the reason the power loss and thus heat and thermal problem are minimized, but it requires smart real-time control. So it's just a suggestion for the researcher and presenter.
For me, I think I can answer this one.
Yeah.
Yeah, actually, like when we talk about soft switching, we always consider like we have no loss. We only have the conduction loss on the GAN device. But in the real application, it's not true. Because of the dead time.
That type problem. That type value. Yes. Okay, I agree.
Yeah.
Okay. If we have a detailed discussion, Dr. Dương Trần, we very happy if you can contact us or we contact you for the more discussion and detailed investigation in the future work. Okay, thank you very much, Mr. Bang and Dr. Dũng for nice presentation and detailed explanation. Okay. And the next presenter is Dr. Phạm Văn Long from Tokyo Metropolitan University, Japan.